Hi, my name is Arushad Ahmed. I'm a recent graduate of University of St. Andrews. So this was part of the work I did for my master's dissertation. So my paper is on improving Dhivehi automatic speech recognition with subword modeling, language model decoding, and automatic spelling correction. So first, I'll talk a little bit about my motivation. So automatic speech recognition is basically the process of automatically converting spoken language into text. This is various applications, especially for such as accessibility applications and other applications as well. Modern ASR systems typically use end-to-end architectures, and recent state-of-the-art models has typically been multilingual. These multilingual models usually produce very good results on high-resource languages. However, for low-resource languages like Dhivehi, there's room for improvement as these models can benefit from language-specific optimizations and fine-tuning. So maybe you might not be familiar with Dhivehi. So Dhivehi is the language spoken in the models. So I'm a native speaker of the language. There is only around 340,000 native speakers for this language. So Dhivehi is written from the right to left and in the Tana script. So the Tana script has vowel diacritics and consonant letters. So the vowels appear either above or below the consonants, as you can see from this sentence that's written here. So to make a sound in the Dhivehi language, you need to combine vowel and consonant together. So when a vowel or consonant appear by themselves, they do not actually produce any sound. So this will become apparent during our optimization or strategies later on. So next we'll look at different ASR model architectures. So one architecture is connectionist temporal classification or CTC based model. So this is an explicit alignment model, which essentially learns mapping from different aspects of speech to output character sequences over an output vocabulary. These models are kind of dumb in a way, as they don't have any knowledge about the syntax or the semantics of the language. Sequence to sequence based models or encoder decoder models, on the other hand, they take an input audio sequence and based on that, on context vectors, they produce an output text sequence. So these models, on the other hand, are a bit more smarter, as in they implicitly learn a language model over the training transcripts. So there are different ways of boost accuracies of these models, especially for CTC-based models. You can use an external language model, such as a transformer-based model or even an n-gram-based model, which can be incorporated into the CTC decoding process to boost accuracy. And also, previous research has shown that this language model decoding results can be further improved by using automatic spelling correction, such as using a text transform model. And also, it's very important for the CTC output vocabulary to mesh the phonetic characteristics of the target language. So instead of using like character-based vocabulary, if your output vocabulary consists of subwords, this also been shown to improve the accuracy. Sequence to sequence or AD models benefit less from these techniques, but they can also benefit from language-specific fine-tuning. There has been some past works done on Dhivehi ASR. Most of the works has been done as part of evaluating multilingual models on under-resourced languages. So specifically like Tiazen, Maya, Fairmetal, and Humetal. They were able to obtain wide error rates around 66 to 54%. So here the lower number is better. And all of these models has been trained on data from the Mozilla Common Voice speech dataset. So the current state-of-the-art ASR model can be considered as a fine-tuned version of XLSR, which is basically a multilingual version of Web 2.0. So this was trained on 25 hours of speech and was able to achieve a word error rate of 21.23%. So for our system, first we chose different SR pretrained SR models for fine tuning. So with the three models, we chose XLSR, MMS, and Whisper. So XLSR and MMS are basically multilingual versions of Web 2.0. So MMS has been pre-trained on around 1,000 languages, and XLSR were pre-trained on around 53 languages. The XLSR and MMS models are basically CTC-based models, and we chose the 1 billion parameter checkpoints for both of them. And Whisper is a transformer-based sequence-to-sequence model, and we chose Whisper Small for fine-tuning. Next, we decided to try using two different CTC output vocabularies to train the CTC-based models. So for the character-based vocabularies, this is what was used by previous works. They had essentially used all the different 49 Tana symbols. Additionally, they used two Arabic ligatures that commonly appear in Dhivehi text. However, this character-based output tokens do not directly correspond to any phonemes, as a vowel or consonant by itself doesn't produce any sound in the language as mentioned before. So we decided to model a new subword-based vocabulary. So for this vocabulary, we had used all the Tana consonants and aforementioned two Arabic ligatures. Additionally, we included all consonant vowel pairs. However, we decided to not include vowel diacritics by themselves, as they do not correspond to any sound. And here you can see like a sample text which has been tokenized first using the character-based vocabulary and next using the subword-based vocabulary. And if you can read the, you can see for the subword-based vocabulary, you can actually pronounce these tokens. So how you would pronounce this would be E through like this. But for the character-based one, you can't actually make any sound based on the tokens. And next, we look at the speech data set which was used for training. So we had also decided to use Mozilla Common Voice so that we can have a direct comparison with previous works. So for this, for our models, we had chosen Mozilla Common Voice version 13.0. For training, we had combined the train and other splits from Common Voice, and which was in total around 25 hours of training data. And for evaluation during the training, we had used a validation set of around 3 hours. And for the final model evaluation, we had used a test set of 3 hours and 21 minutes. Next, for training our language models and automatic spelling correction models, we needed a text corpus. There's not many Dhivehi text corpora available in the public, so we had to create a new one. So this was created from around 4.2 gigabytes of Dhivehi text that were expected from around 1 million news articles provided by Archive.me, which is Models Online News Archive. Then we extracted sentences from these news articles using NLTK and normalized them to remove punctuation and replaced multiple white spaces with single spaces. In the final corpus, we had around 18 million sentences. And for training our automatic spelling correction model, we needed the pre-trained text-based model. So we chose the Unimax model, which is the multilingual version of the T5 text-to-text transform model, and we chose the T5 small checkpoint, which is around 300 million parameters. For our implementation, we had trained in total 5 different ASR models. So for each of the CTC-based models, we had one with the character-based vocabulary and one with the subword-based vocabulary. And for these models, we trained for around 30 epochs, except for this MMS-based subword model, which we trained for additional 40 epochs. And for the Whisper model, we trained for 15 epochs. And all of the training were performed on the RTX 3090 Ti. Then here are the language models we trained. We trained 2 language models, which were both 5-gram models. One of the models, there was no restriction during training. And for the other model, we had restricted the vocabulary to 500,000 common words. And we used ICNLSP for training these models. And to train the spelling correction models, first we had to create 2 synthetic data sets. This was done by taking random text samples from the Archive.me corpus, and we introduced synthetic spelling mistakes into that. So these spelling mistakes were designed to mimic the errors that were observed in the ASR model outputs. So these included randomly removing spaces, randomly inserting characters at the end of sentences, and interchanging particularly similar letters, and random insertion, deletions, and different modifications of characters. And we had created one data set with around 1 million samples and another second data set with around 10 million samples. So one model was trained with the 1 million sample data set, and the other model was trained with 10 million data set. And for evaluation, we had created the third data set by taking the MMS-based subword model outputs, decoding using the academic 5-gram language model. For our evaluation, first we'll look at our baseline results. So this is done without any of the language model decoding or spelling correction. So we are comparing against the state-of-the-art Dhivehi model. And this evaluation was performed on the test set of Mozilla Common Voice version 13. And here you can see our MMS-based subword model was able to beat the state-of-the-art model, and we were able to get a word error rate of 16.19, which is a relative improvement of 22.72% over the state-of-the-art. And more interestingly, you can see that our subword-based models performed much better. In fact, on average, they were able to improve the word error rate by 61.79% as compared to the CTC models which use the character-based vocabulary. And also, we can see Whisper Small generally performed worse, I guess, compared to the subword-based CTC models. And here you can see like a sample utterance that has been transcribed using the MMS-based subword model, and you can see only a few errors in the predicted text. Next, we'll look at our language model decoding results. We are comparing the two different language models, and you can say from here, the language model decoding is able to further improve the word error rate of the CTC-based models. And you can see from the two language models, the language model that didn't have any vocabulary restrictions or limitations performed overall better. On average, that model was able to improve the word error rate by 5.65% across all the different CTC-based models. And our best performing model had a relative improvement of 10.50%. And this is the same sentence as before, now transcribed with language model decoding with our best performing language model. And you can see even like less errors in the predicted text. Next, we'll look at our spelling correction results using our two different spelling correction models. Here you can see, so here is the baseline for the CTC-based models. We have taken the outputs from the academic 5-gram language model decoding and use that as input, and we're comparing the word error rate against it. And for the Whisper model, we are comparing it against the normalized text outputs from the model, because we didn't use English model decoding for Whisper. And here you can see that the model that was trained on 1 million samples actually wasn't able to improve the word error rate overall at all. However, for the model that was trained on 10 million samples, was able to slightly improve the word error rate estimate, but it's only like a slight improvement. And here you can observe that for the Whisper model, it has the least improvement. This is expected as it's a sequence-to-sequence model, which essentially has an internal language model, so it benefits less. And now you can see the same sentence as before. Now this is with both language model decoding and spelling correction. You can see there's only maybe one error in the output. So overall, using both language model decoding with our best language model and spelling correction, our LMS-based subword based model reduce the word error rate to 14.26%, which is the new state of the art for Mozilla Common Voice version 13 benchmark. This is a 31.93% relative word error rate improvement as compared to the 20.95% word error rate of the state of the art Dhivehi model. Overall, spelling correction in addition to language model recording is able to boost the accuracy of CTC-based models. However, the relative improvement going from language model recording to spelling correction is markedly less compared to the relative improvement going from baseline to language model recording. Also, performance spelling correction on top of language model recording adds additional memory overhead and can be around 1.6 times lower than language model recording ever. In conclusion, have a look at some limitations of our work and some possible future work. We need to do further evaluation of these models on out-of-distribution dataset to investigate if they're able to generalize well. Also, the subword-based vocabulary can be expanded further to include the Dhivehi phonics, which has not been included in the current subword-based vocabulary. Also, we could investigate with even more ASR model architectures and also using larger versions of the different pretrained models that we had currently used. Also, I think the biggest limitation is the amount of Dhivehi speech data that is available. So we could potentially use force alignment to generate even larger Dhivehi speech data. So we could potentially improve the word error rate. So in conclusion, we can say that pre-trained multilingual ASR models can greatly benefit from language-specific fine-tuning and optimization, and especially for CTC-based models, it's proposed Subword Modelling and language model recording seems very crucial. AD models seem to benefit less from this accuracy boosting techniques, but they can also benefit from language-specific fine-tuning. So that's all for my talk. Thank you.